Okay, hoping that that is a relatively good angle. My battery died in my phone, so I had to plug into the wall here. So it's kind of a strange angle. But we're showing that the matrices whose rows add up to 0 is a subspace. We checked closure under addition here, and we checked closure under scalar multiplication here. And now I'm asking for a basis for that set. So here's a typical matrix, right? Capital A, that's a typical matrix in the set. So can somebody tell me how did you get the basis? Exactly, you bust out the variables of that thing. So we're just going to take the matrix A. How many variables do I have to bust out? 4 of them. So if I bust out the A, I'm going to get 1, 0, negative 1, 0, 0, 0. And then when I bust out the B, I'll get 0, 1, negative 1, 0, 0, 0. And I bust out the C, I get 0, 0, 0, 1, 0, negative 1. And finally, when I bust out the D, I get 0, 0, 0, 0, 1, negative 1. Okay, so my basis is just the 4 matrices that you have come up with here. So you just have to write them out. 0, 1, negative 1, 0, 0, 0. And then 0, 1, negative 1, 0, 0, 0. 0, 0, 0, 1, 0, negative 1. And 0, 0, 0, 0, 1, negative 1. There we go. What's the dimension of S? 4, right? There's four vectors in S. Okay. Good enough? Does that make sense? All right, let's move on. So we've done a lot of examples checking subspaces in different contexts, and that's definitely something to keep practicing on. Let's spend a little bit more time just doing a few other things. Okay, let's do this one. Another type of problem. This time I'm going to give you a set of vectors and ask you whether they are Li, a spanning set, both, or neither. Okay? So let's let V equal M2 of R. And let's let S be the set that has the matrix 1, negative 3, 6, 1. And then 2, 1, 0, 4. And then negative 1, negative 1, 2, and 1. Okay? And what I want to ask is S Li spanning set, both, or neither? This is the question. So we've been just practicing this recently, right? So the idea here is you should be able to cross off 2 of the 4 choices immediately just by looking at what V is and how many vectors you have. What is the so what do we need to look at here, guys? Okay, the dimension of V and the number of vectors. What is the dimension of M2 of R? 4, right? And then the number of vectors is what I was calling K in my notes the other day. And what does K equal to here? 3. That's just the number of vectors that we have. So you just need to remember now, what does that tell you? If the K is less than the dimension, then what do you know about these vectors? Right, it cannot span, which means, of course, it's also not both. And it might be Li. It might be Li. So the real question is whether or not these vectors are Li, and how am I going to test that? Exactly. I put these vectors into a matrix, and how do we put them into a matrix?
As long as you keep it consistent, so you can do 1,
columns.
negative 3, 6, yeah, columns.
Right, so you put them into the columns of the matrix, and as long as you do the 4 entries in a consistent order, I usually go left to right, top to bottom. So 1, -3, 6, 1, and then the second matrix in the second column would be 2, 1, 0, 4. Third matrix in the third column, -1, -1, 2, and 1. And I would augment that with what if I'm testing for Li?
Zeros.
All zeros, exactly. So 0, 0, 0, and 0. Okay, and we just have to row reduce this now. So I'll just do this pretty quickly. The first row, of course, will stay the same. I'm going to take 3 times the first row and add that to the second row. So 0, 7, -4, and 0. And then -6 times the first row, I'm going to add that to the third row. And the negative of the first row, I'll add that to the bottom row. I think this is what I get. And you can already tell, that, so the first 2 columns are going to have pivots, and you can tell that when you zero out the numbers below the 7s, you're not going to get zeros here and here. So you kind of know, I'll skip the actual details of the EROs, but you kind of know that ultimately there will be a pivot here. Is it okay if I do that? Just make sure you're careful with that, because it really isn't a pivot in the way I've written the matrix. There's still a number here. But anyway, so this should be 3 columns that all have pivots, so there are no free variables. And so it is Li. Right? So the correct answer would be S is Li this time on this one. Does that make sense? If the matrix that you have as your coefficient matrix is square size, you could just use the determinant, and you have like a both or neither scenario. So if the determinant is not 0, then it's both. If it is 0, then it's neither. So yeah, I feel like we've gone over that pretty well already. Linear independence. Well, actually, let me do one more of these kind of problems, and then I think we might be in pretty good shape. Let's just do one more example to kind of wrap this up. So let's do this one. This one is a little different. That's why I want to do it. Let's say we use V equals P3 of R, and S is the set of polynomials 1 plus x plus 3x squared plus 3x cubed, comma, x plus x squared, comma, 2 minus x plus x cubed, comma, -3 plus 6x plus 6x squared plus x cubed. So let's take that example. Okay, see if we can figure this one out. What is the dimension of V? Right, so the dimension of the vector space is 4. What is the k value? There's 4 vectors, right? So k equals n. So that means it's going to give me a square matrix, and the answer is either both or neither. By the way, we're asking the same question. Okay, so it's both or neither. By the way, neither is always an option. I've seen people do this before. They say, oh, since these numbers are different, it's not both or neither. Like I'll see, if k does not equal n, people will come over and say, oh, it's not both or neither, and they'll cross off neither. And I'm like, no, you can never cross off neither. Right? Neither is always an option. Okay, so here we're going to again put our vectors into the matrix in columns. So the first polynomial, the coefficients are 1, 1, 3, and 3. The second one is 0, 1, 1, and 0. The third one is 2, -1, 0, and 1. And the last one is -3, 6, 6, and 1. And that is a square matrix. we could take the determinant of it. I'm going to tell you what that is just to save a little time, unless you would like me to review that again. Is everybody good with if I just, so it is 0. It is 0. So if you believe me that I did it correctly and that it is 0, then you would conclude that it's neither, right? But I want to add a follow-up, which is, so it is neither. It's not a basis, it's not Li, it's not a spanning set. But I do want to follow up. I'm going to ask maybe 2 follow-ups. I've got a couple follow-ups in mind. I would like to, you guys have to go?
Yeah, we have 2 times.
Okay, let me write down the questions I'm going to do, and then you guys can watch the video later. Okay, so because I know you need to go. So my follow-up question, there's 2 follow-ups, and I'm going to stay a few extra minutes to do this for those of you who can stay. The first one is find a linear dependency. Find a linear dependency among S. And then the second follow-up would be find a basis for the span of S. So we know that S does not span the whole P3 of R, but it obviously spans whatever it spans, which is some subspace of P3 of R. And I would like a basis for that. That subspace, of course, will not be 4-dimensional. It'll be smaller. So these 4 vectors are not a basis for anything because they are LD. So we would have to remove. So basically on part B, I'm asking you to remove vectors that are linearly dependent. These 2 questions are related. Okay? So I know a few of you may have to go, but I'll go ahead and solve this for those of you who can stay just 5 more minutes. What are you going to do to find the linear dependency here? Right, you actually have to then row reduce this matrix. So you would actually, so for part A, you would have to just row reduce this matrix. So you would just take 1, 0, 2, negative 3, and 1, 1, negative 1, 6, and then 3, 1, 0, 6, and then 3, 0, 1, 1, and you would row reduce this one. Okay, maybe will you guys let me just tell you the row echelon form? Would that be all right? Just to kind of move it along here. So the row echelon form of this is 1, 0, 2, negative 3 augmented with 0, and then the second row becomes 0, 1, negative 3, 9, and 0. The third row is 0, 0, 1, negative 2, and 0. And the last row completely zeroes out. Okay, so your pivots are here, 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 and here, and you can now see the linear dependency. It's coming from the last column. So remember that usually we think of the constants as C1, C2, C3, C4. In this case, C4 is free. So C4 would be equal to T. I'll call it T for my free variable here. And then from the previous line, so the third line of the matrix, C3 minus 2T equals 0. So C3 is just going to be 2T, right? So just using the third row. And then we have to back substitute from there. So C2 is going to equal 3 times C3, which would be 6T, minus 9T, that would be negative 3T. Okay, and then finally we have to back substitute into the very first equation to get C1. C1 would be negative 2 times C3, which would be negative 4T, and then plus 3T, that would be negative T. There we go. So we come up with this solution, and what do I do now to get my linear dependency? Do you remember? I have to choose a number for T, right? So I might choose t equal to, what's your favorite number besides 0? Don't choose 0. 1. Okay, so choose t equals to 1 exactly. So then what will happen is the linear dependency is just, c1 v1 plus c2 v2 plus c3 v3 plus c4 v4. So we have -1 times the first polynomial, 1 plus x plus 3x squared plus 3x cubed. And then, what is it, -3 times the second polynomial. And then plus 2 times the third polynomial. And then plus 1 times the last polynomial. And all of that adds up to 0. So this is the linear dependency that you have. So it says find a linear dependency. This would be the equation. Does that make sense? That's how you create the linear dependency. And then
The basis would just be the polynomials, right?
which polynomials?
It'd be the 1 plus x plus 3. No, because we just said that it wasn't. Never mind.
So these 4 polynomials are LD. But if I want to get a basis for the span of whatever, so in other words, I'm asking for a basis for the span of this.
So you would just take out the fourth one. Right?
Exactly. I just have to throw away, we did one like this in class, I just have to throw away, it's the 4th vector that is causing all the problems, right? The 4th vector is the one that leads to an unpivoted column in the matrix. And if I got rid of that 4th vector, right, if I got rid of that 4th vector, then I would have no free variables anymore. So you're gonna, your answer for part B is you just simply have to write down these vectors here. So this is it. Plus x squared, 2 minus x plus x cubed, and that's it. Those 3 vectors right there. So finding spanning sets, linear dependencies, asking whether something's a basis or not, these are good things to be reviewing. Does everybody understand these problems okay? Not bad for now anyway. All right, well, hey, that was exactly the right amount of time. I'm going to take a break for a while until I have another review later today. So anyway, thank you guys for coming, and we still have some homework to do too, don't we?